Hello. In this video, we will be talking about an active suspension system that is applied in cars to create a better handling and ride experience. The system we are talking about today is a magnet rheological fluid-based system or a ferrofluid-based system.
Here we can see that as a car turns down a road, the body rolls side to side. This is because of loose or soft dampening of a car suspension, which transfers the force of the wheels to the body of the car. Soft suspensions give a more comfortable ride over bumps and divots, but perform poorly in turns because the impulse imparted on the body of the car is too weak to accelerate the body of the car at the same rates as the wheels. The result is an uncomfortable ride that can compromise turning performance.
This is a schematic of the dynamic system as it is represented in the car. We can see all the components that go into the suspension system. Inputs from the suspension and the body contribute in creating a system that is stable. To help mitigate the effects of body roll, engineers created a system that upon turning, braking, or acceleration, the suspension dampers located on the outside of a turn stiffen and allow for a proper response to a turn.
Looking into the dampers themselves, there is an electromagnet inside each of the monotube piston dampers located on the piston head. The piston is filled with a synthetic oil with magnetic particles 3 to 10 thousandths of a millimeter in diameter. As shock is received from the road, oil passes through the piston head in small channels. When the electromagnet has current pass through it, the magnetic particles align with the field lines, increasing the viscosity of the fluid.
In this clip, blue lines indicate inputs into the system. These inputs include measuring steering wheel position, using accelerometers to measure body roll, and using distance sensor to find displacement of the suspension from standard ride height. The system control unit then performs calculations and sends feedback in the form of variable currents to control the strength of the active dampening system. The system is controlled continuously by taking hundreds of measurements every second and sending commands to the suspension assembly.
This is the simulated block diagram of the system, which is controlled by a specialized PID controller. The PID does not have a single setting but multiple inputs to determine the values of its P, I, and D coefficients. These inputs include user settings, steering wheel inputs, and other vehicle stability control parameters. For steady forces imparted on the system, in maneuvers such as turning, the proportional term is increased to decrease the current state of error until the deflection returns to zero. For highly unstable or bumpy rides, such as driving over cobblestones, the integrator term is decreased to give a softer ride by decreasing the speed of the controller's reaction to deflection. The derivatives term increases stability and prevents oscillation. The derivative term would be increased when going over a speed bump to prevent oscillation of the car body after the speed bump is over.
The car's drive mode selector plays an important role in the operation of the P, I, and D terms of the controller. Looking at the luxury versus sport mode, the sport mode will have an increased proportional value which affects the aggressiveness of the response. The mode selection will affect the ratio of I to D strength, with the sport mode favoring a stronger P to D ratio and the luxury mode favoring a stronger D to P ratio.
Overall, the system aims to create different ride experiences with the push of a button. Desired performance metrics can be changed either by selecting sport mode for aggressive turns or comfort for long-haul touring. The system has a comparable edge over passive systems in safety, as well as allowing for aggressive turns without compromising surface contact. To become a further expert in actively controlled suspension systems, please contact Professor Eric Meal.